Welcome back to the Comptia Network Plus course. Neighbour table. Each router keeps state information about adjacent neighbours. When a newly discovered neighbour is learned on a router interface, the address and interface of that neighbour are recorded, and the information is held in the neighbour table and stored in RAM. Sequence numbers are used to match acknowledgements with update packets. The last sequence number received from the neighbour is recorded so that out of order packets can be detected. Topology table. The topology table is populated by the neighbour table, and the best path to each remote network is found by running diffusing update algorithm dual. The topology table contains all destinations advertised by neighbouring routers, holding each destination address and a list of neighbours that have advertised the destination. For each neighbour, the advertised metric, which comes only from the neighbour's routing table, is recorded. If the neighbour is advertising this destination, it must be using the route to forward packets. Successor routes in a routing table. A successor route is the best route to a remote network. A successor route is used by EIGRP to forward traffic to a destination and is stored in the routing table. It is backed up by a feasible successor route that is stored in the topology table if one is available. Feasible successor backup routes. A feasible successor is a path considered a backup route. EIGRP will keep up to 6 feasible successors in the topology table. Only the one with the best metric, the successor, is copied and placed in the routing table. By using the feasible distance and having feasible successors in the topology table as backup links, EIGRP allows the network to converge instantly, and updates to any neighbour only consist of traffic sent from EIGRP. All of these things make for a very fast, scalable, fault-tolerant routing protocol. BGP, Border Gateway Protocol. In a way, you can think of Border Gateway Protocol, GP, as the heavyweight of routing protocols. This is an external routing protocol used between autonomous systems like Routing Internet Protocol, Open Shortest Path, the first, which are internal routing protocols that uses a sophisticated algorithm to determine the best route. In fact, it just happens to be the core routing protocol of the internet, and it's not exactly breaking news that the internet has become a vital resource in so many organizations. It is, but no. But this is growing dependency has resulted in redundant connections to many different ISPs. This is where BGP comes in. The sheer onslaught of multiple connections will totally overwhelm other routing protocols like OSPF, which I'm going to talk about shortly. Border Gateway Protocol is essentially an alternative to using default routes for controlling path selection. Default routes are configured on routers to control packets that have a destination IP address that is not found in the routing table. Because the internet's growth rate shows no signs of slowing, ISPs use Border Gateway Protocol for its ability to make classless routing and summarization possible. These capabilities help to keep routing tables smaller and more efficient at the ISP core. Border Gateway Protocol is used for IGPs to connect ASs together in larger networks if needed, as shown in figure 10.8. So here we figure 10.8 Border Gateway Protocol BGP, and here we just have routers Autonomous System 1 EGP Border Gateway Protocol, and here we have routers with Autonomous System 2. So yes, very large private networks can make use of Border Gateway protocols. Let's say you wanted to join a number of large OSPF networks together. Because open shortest path first just couldn't scale up enough to handle such a huge load. You would want to go with Border Gateway Protocol instead to connect the AS together. Another situation in which Border Gateway Protocol would come in really handy is if you wanted to multi-home a network for better redundancy, either to a multiple access point of a single ISP or multiple ISPs. Internal routing protocols are employed to advertise on all available networks, including the metric necessary to get each of them. Border Gateway Protocol is a personal favourite of mine because it routes exchange path vectors that give you detailed information on the Border Gateway Protocol. AS numbers hop by hop, called an AS path, required to reach a specific destination network. Also good to know is that Border Gateway Protocol doesn't broadcast its entire routing table like Routing Internet Protocol does. It updates a lot more like open shortest path first, which is a huge advantage. Also, the routing table with Border Gateway Protocol is called Routing Information Base (RIB), and Border Gateway Protocol also tells you about all networks reachable at the end of that path. These factors are the biggest differences you need to remember about Border Gateway Protocol. Unlike interior gateway protocols that simply tell you how to get to a specific network, Border Gateway Protocol gives you a big picture on exactly what's involved in getting to an AS, including the networks located in that AS itself. And there's more to that Border Gateway Protocol big picture. This protocol carries information like the network prefixes found in the AS and includes IP address needed to get to the next AS, the next hop attribute. It gives you the history of how networks at the end of the path were introduced into Border Gateway Protocol in the first place, known as the origin code attribute. All of these traits are what makes Border Gateway Protocol so useful for constructing graph and loop-free autonomous systems, for identifying routing policies, and for enabling us to create and enforce restrictions on routing behavior based on the AS path. Link state routing protocols. Link state protocols also fall into the classless category of routing protocols. They work within packet switched networks. OSPF, IS are two examples of link state protocols. Remember, for a protocol to be a classless routing protocol, the subnet mask information must be carried with the routing update. This enables every router to identify the best route to each and every network, even those that don't use class-defined default subnet masks, i.e. 8, 16 or 24 bits, such as VLSM networks. All neighbor routers know the cost of the network route that's being advertised. One of the biggest differences between link state and distance vector protocols is that link state protocols learn and maintain much more information about the internetwork than distance vector routing protocols do. Distance vector routing protocols only maintain routing tables with the destination routes and vector cost like hop counts in them. Link state routing protocols maintain two additional tables with more detailed information, with the first of these being the neighbor table. The neighbor table is maintained through the use of hello packets that are exchanged by all routers to determine which other routers are available to exchange routing data with. All routers that can share routing information are stored in the routing table. The second table maintained is the topology table, which is built and sustained through the use of link state advertisements or packets, LSAs or LSPs. In the topology table, you'll find a listing for every destination network plus every neighbour route through which it can be reached. Essentially, it's a map of the entire internetwork. Once all of that raw data is shared, and each one of the routers has the data in its topology table, the routing table runs the shortest path first SPF algorithm to compare it all and determine the best paths to each of the destination networks. Open shortest path first, OSPF. OSPF is an open standard routing protocol that's been implemented by a wide variety of network vendors including Cisco. OSPF works by using Dijkstra algorithm. First, a shortest path tree is constructed, and then the routing table is populated with the resulting best paths. OSPF converges quickly, although not as fast as EIGRP, and it supports multiple equal cost routes to the same destination. Like EIGRP, it supports both IP and IP version 6 route protocols, but OSPF must maintain a separate database and routing table for each, meaning you're basically running two protocols if you are using IP and IP version 6 with OSPF. OSPF provides the following features: consists of areas and autonomous systems, minimizes routing update traffic, allows scalability, supports VLSM, CIDR, has unlimited hop count, allows multi-vendor deployment, open standard, uses a loop-back logical interface to keep the network stable. OSPF is the first link state routing protocol that most people are introduced to, so it's a good idea to see how it compares to more traditional distance vector protocols like Routing Internet Protocol version 2 and Routing Internet Protocol version 1. Table 10 tree gives you a comparison of these three protocols. Table 10 tree OSPF and RIP comparison. Characteristic: OSPF Routing Internet Protocol version 2, Routing Internet Protocol version 1. Type of protocol: link state, distance vector. Classless support: yes, yes, no. VLSM support: yes, yes, no. Auto summarization: no, yes, yes. Multiple manual summarization: yes, no, no. Discontinuous support: yes, yes, no. Route propagation: multicast on change, multicast on change, multicast on change. Path metric: bandwidth, hops, hop count, num 15. Convergence: fast, slow. Peer authentication: yes, no. Hierarchical network updates: yes. Using areas: no, flat only. Updates: event triggered. Route table updates: time intervals. Route table updates. Route comparison: Dijkstra, Bellman Ford. OSPF has many features beyond the few I've listed in Table 10 tree, and all of them contribute to a fast, scalable and robust protocol that can be actively deployed in thousands of production networks. One of OSPF's most noteworthy feature is that after a network change, such as when a link changes to up or down. OSPF converges with serious speed. In fact, it's the fastest of any of the interior routing protocols we'll be covering. Just to make sure you're clear, convergence refers to when all routers have been successfully updated with the change. OSPF is supported to be designed in a hierarchical fashion, which is definitely the best design for OSPF. The following are reasons you really want to create OSPF in a hierarchical design: to decrease routing overhead, to speed up convergence, to confine network instability to single areas of the network. Figure 10.9 shows a typical OSPF simple design. Notice how each router connects to the backbone called area 0 or the backbone area. OSPF must have an area 0 and all other areas should connect to this area. Routers that connect other areas to the backbone are within an AS area called area border routers, ABRs. Still, at least one interface of the ABR must be in area 0. So here we go, area 0 backbone router, area 1 area border router, ABR, and autonomous system border router, ASBR. OSPF runs inside an autonomous system, but it can also connect multiple autonomous systems together. The router that connects these ASs is called an autonomous system border router, OSBR. Typically in today's networks, border gateway protocol is used to connect between ASs and not open shortest path first. Ideally, you would want to create other areas of networks to help keep route updates to a minimum and to keep problems from propagating throughout the network. Intermediate system to intermediate system. ISIS is an IGP, meaning that it's intended for use within an administrative domain or network, not for routing between ASs. That would also be a job that an external gateway protocol such as BGP, which we just covered, would handle instead. ISIS is a link state routing protocol, meaning that it operates by reliably flooding topology information throughout a network of routers. Each router then independently builds a picture of the network's topology, just as they do with OSPF. Packets and datagrams are forwarded based on the best topology path throughout the network to the destination. Figure 10.10 shows an ISIS network and the terminology used with ISIS. Here are the definitions for the terms used in the ISIS network shown in figure 10.10. L1 level 1 intermediate systems route within the area. When the destination is outside an area, they route toward a level 2 system. L2 level 2 intermediate systems route between areas and towards other ASs. So here we have the figure, ISIS network terminology. So that's the picture there. The similarity between ISIS and open shortest path first is that they both deploy the Dijkstra's algorithm to discover the shortest path throughout the network to a destination network. The difference between ISIS and open shortest path first is that ISIS uses connectionless network service, CLNS, to provide connectionless delivery of data packets between routers. It also doesn't require an area like 0 like OSPF does. OSPF uses IP to communicate between routers instead. An advantage to having CLNS around is that it can easily send information about multiple routing protocols, IP and IP version 6. And as I've already mentioned, OSPF must maintain a completely different routing database from IP and IP version 6 respectively for it to be able to send updates for both protocols. ISIS supports the most important characteristics of Open Shortest Path First and Enhanced Interior Gateway Protocol because it supports VLSM and also because it converges quickly. Each of these three protocols has advantages and disadvantages, but these two shared features that make any of them scalable and appropriate for supporting large-scale networks for today. One last thing, even though it's not common, ISIS, although comparable to Open Shortest Path First, is actually preferred by internet service providers because of its ability to run IP and IP version 6 without creating a separate database for each protocol as OSPF does. That single feature makes it more efficient in very large networks. So I'm going to leave it here today for this video. If you like listening, please consider sharing and subscribing. Thank you.